Hi everybody, my name is Cameron and today we're going to be looking at light in a bit more detail. We're going to be looking at the law of reflection of light, we're going to be looking at refraction of light, light in color, as well as lenses and how they're going to change the direction of light. So when we look at the law of reflection, basically what this is saying is light consists of waves, specifically these electromagnetic waves that we spoke about in the last lesson. So when they hit a flat barrier, they are going to be reflected at the same angle to the barrier as the incident wave is to the barrier. So what does that mean exactly? Basically, the wave coming in, is going to have a certain angle. Now we take that angle as the angle between the wave coming in and something called the normal. Now the normal is a line, an imaginary line that we draw that's perpendicular, to our surface, as we can see here. So that line is perpendicular and the angle of incidence is going to be the angle at which the light is coming in and the normal. Between those two lines, angle of incidence. The angle of reflection is going to be the reflected ray, and the normal between those two. And what the law of reflection is basically saying is the angle of incidence is going to equal the angle of reflection. That's it. So let's look at image formation. It's pretty obvious stuff, but it's important for you to sort of know the terminology. So an image, the image and the object are at equal distances from the mirror. What does that mean exactly? The distance to object is that you're looking at, so we're looking through a mirror, and we're looking at an object that's next to us, but we can see it because of the mirror, or behind us, let's say. So the object's behind us, but I can see it because I'm looking in the mirror. The distance between that object and the mirror is the same distance as the mirror and the image that you are seeing. Because you are not seeing that object, you're seeing an image of that object, you see. And that's why it's really cool when they have these gun people that shoot guns, or bows and arrows. They can look in a mirror and they can go bang, and they can shoot something behind them by just looking in a mirror, because that object is the same distance away from the actual person in the mirror. You see that? So the image formed by a plane mirror is virtual. Again, an image. You see that? It's a virtual image, even though it's a mirror. It's not actually there, it's behind you. But the image we're seeing is virtual. It's upright, so it still stands upright, but it is laterally inverted. So go to a mirror, write something down on a piece of paper, and look at that piece of paper in the mirror. You'll see the words are back to front because it is laterally inverted in a mirror. Now, an image that can be seen on a screen, however, is described as a real image because it is formed by focusing light rays onto the screen. That's why you can take a picture of someone's shirt and it doesn't look like their shirt's writing is back to front. You see, it's not a reflection of the person on the screen. It is an image that is focused light onto the screen. So reflection from a smooth surface is called specular reflection because the parallel rays are reflected in a single direction. Now, reflection from a rough surface is called diffuse reflection because the light is scattered in different directions. So if you've ever been to one of those places that has a mirror that'll make you look very wide, or a mirror that'll make you look very tall, or a mirror that'll make you look very squashed, that's because it is diffuse reflection. It's not a flat mirror. So let's look at refraction of light now. We talked about this a bit in the previous lesson. So refraction occurs when you have light that is entering a different medium through a barrier. So when how lenses of glasses work, anything like that, what it is doing is changing the direction of the light because of the shape for one, and we'll get into that when we do concave and convex lenses, but also because of the medium that is traveling through. Now, theoretically, as it leaves that medium, it should be going at the same angle as it was coming in. You see that? So as we can see in this picture here, the air sides, both air sides, are coming in at the same angle and leaving at the same angle. Okay. Now, why that is? So when light rays refract as it travels from air, from a less dense to a more dense, the angle of refraction is less than the angle of incidence. Okay. So when you have light coming in, it is going to bend towards the normal. That makes the angle of refraction less than the angle of incidence. Okay. When it is leaving the glass or the water or whatever, it is going to travel away. So the angle of incidence, the new angle of incidence that is in the glass, okay, is going to be less than the angle of refraction when it is leaving into a less dense glass. Okay. So how does color work exactly? Well, each light, okay, so we know that light is electromagnetic waves. Those waves can have different wavelengths and different frequencies. Now, depending on a light's wavelength and frequency, it's going to have a different color. Okay, it's going to be carrying a certain frequency that is going to be picked up by our eyes, the cones on our retina, and is going to be perceived as a certain color. Okay, so how exactly is color emitted? Where does it come from? Okay, if you look around you, the color that you're seeing right now is all from something called white light. This white light is emitted from the sun. It has all the wavelengths of color in it. It looks white. Okay. Now, it depends on an object of what light is going to be absorbed and what light is going to be reflected. This is due to something called pigments. Okay. So whenever we see anything that is slightly see-through or something that reflects light, it's going to be because of pigments. So right now, the wall behind me is green. Okay. But it's actually not green per se. It's absorbing every other color except for green. And that green is being reflected off the wall because of the green pigments that it's made up of. That green is then the only light coming into my eyes right now, and I can see it. And the same goes for every color around us. Really interesting stuff. And of course, that green is going to have a different wavelength, a different frequency as well, to the top I'm wearing. Okay, and therefore my eyes are able to distinguish green and blue. Okay, so when it comes to objects and how we classify them depending on how much light they allow through, we start with transparent. So transparent objects emit all incident light that enters the object. Okay, so they transmit it, they allow it through. They don't reflect anything or very little. Okay, so no light is absorbed and is completely see-through, something like glass. Then we get translucent. Now, translucent are objects that let light pass through, but it scatters it and refracts it. Okay, the material of the object has lots of interval boundaries that change the direction of the light waves. Some plastics and frosted windows. It's actually really cool as well. If you have the time, go on YouTube and go look for quantum stealth invisibility cloak. Really cool. It's something that is going to refract the light of an object that's behind it, so it looks like the object isn't there, even though it's allowing light through and the object should be seen. Okay. Then we get opaque. Opaque objects that absorb all the light that reaches it. Okay, so no light goes through. This is something like wood. This is something like me and you, the wall behind me. Okay, these would be considered opaque. So when it comes to lenses now, okay, a lens works by changing the direction of light passing through it. That's what I said earlier, right? Now we get two different types, convex and concave. Okay, So convex is kind of like a leaf shape, okay? And this is also known as a converging lens, because what it does is it's going to take light, and it's going to converge those parallel light rays, okay? It's going to converge them into a point on the other end of this lens, okay? And this point we call the focal point, okay? And the distance between the focal point and the center of the lens we're going to call the focal length. Okay, now depending on how convex the lens is, okay, if it's narrower or if it's fatter, it's going to change the focal length and the position of the focal point. Okay, so this is used in magnifying glasses as well as cameras. Okay. So the next lens is the concave lens. Concave lenses are kind of inwards, kind of like hourglass shaped. Okay, and what they're going to do is they're going to diverge the light rays. So they're going to have them split off, okay, from being parallel to spread out. Okay, so it doesn't really have a focal point, and it is going to be used to correct short-sighted people. Okay. The focal point here would be, as we can see, it's on the other end, so it's coming from the incidence side, and it is going to be the point of convergence of the two lines, as we see here, if they were coming in the opposite direction. Okay. So obviously when we're using lenses, it's going to be dependent, or the image that we generate is going to be dependent on the focal length of the lens. Okay, so how far the focal point is, the point of convergence of the light rays to the lens, okay, as well as the distance from the object and the lens. Okay, if you have to take an object in a magnifying glass, you'll know that you have to put it in just the right spot to get the maximum amount of magnification, okay, without the object getting blurry. Now it's blurry because we're moving a bit too close to the object. The focal point is no longer hitting our eyes. You see that? And we would have to move a bit further back to get to where the focal point of the magnifying glass is. This is basically what's happening here. Okay, so our object is going to be standing here, an arrow, okay, and we're going to have different rays coming off of it. So ray 1 is parallel to the axis and is refracted through F. Okay. Ray 2 passes straight through the center of the lens, okay, and therefore isn't refracted much. Ray 3 passes through F and is refracted parallel to the axis, and the principal axis of the lens is the straight line that passes along the normal at the center of each lens surface. Okay, so again, it's going to just be a perpendicular line that's going to the lens. Same thing as our normal line in our refraction, because this is refraction, right? Remember that. And the image is real, inverted, and smaller than the object. Okay, so as we can see, these lines are going to represent different parts of the image. So if the lines are coming closer together, it means that image is going to look smaller. If the lines are being diverged further apart than it was originally, it's going to look bigger. Okay, if those lines cross, they are going to invert. They're going to be upside down, which is what's happening here. The lines are crossing, and we are going to see the real image, but further than that, it's going to be inverted. Okay, so just remember, when it comes to formation of virtual images by these lenses, when it comes to convex, it's virtual, upright, and larger than the object. Think of a magnifying glass. And when it's concave, it's going to be virtual, upright, and smaller than the object. Hence why short-sighted people use concave lenses. Okay, so my name's Cameron. This has been Light for a second time, and I will see you in the next lesson.